Hello, my name is Kevin Sloat. This is Sheaves for the People. This video is intended for a very brief introduction of sheaves and sheaf theory for data scientists and engineers. To begin with, we need to get some prerequisites out of the way with a brief introduction to category theory. Let's start with some examples. So we have this top idea, we have topological spaces, and in the theory of topological spaces, we have two topological spaces and then the continuous maps from one topological space to another. Then we also have, for groups, we have that from one group to another, there's a group homomorphism, and this just takes one group to another group. Then for the theory of sets, we have two sets, S1 and S2, and then we have the functions that map S1 to S2. So what mathematicians began to notice is that there's some commonality where we're looking at sets of numbers and different types of sets of numbers together with some sort of map. In addition to these maps from one object to another, we also have this regularity between all of these constructs that the composition of these maps again gives you another one of these types of maps. So in topological spaces, you have two continuous maps. You have X is mapped continuously to Y, and G maps Y continuously to Z. Then you have that the composition of these maps is another continuous function that takes X to Z. Similarly for groups, you have this idea that the composition of two group homomorphisms is another group homomorphism. Similarly for functions of sets, the composition of two set functions is another set function. So this is the motivation behind category theory. All we're looking at when we're studying math, there's this very common phenomena where we're looking at sets of numbers together with maps that take one set of numbers to another, and there's always this compositional principle. So when we define a category, we have objects of the category. So this could be groups, different groups, or in the last example we saw different topological spaces or different sets. And then we have this set of homomorphisms between them, and we call this hom of xy, such that for every two objects we have this property that there's this identity map in this set that takes x back to x. And we also have that these are associative. Sorry, my stupid cat. So this is what the hom set means. And then what we also have is, just for shorthand notation and save on chalk, I'll write as shorthand, I'll say that x is in top, and that's an abusive notation just to say that x is a topological space. Similarly, instead of writing the set of homomorphisms, or hom xy, for two topological spaces, I'll just say top of xy, just so we don't have to write the hom of xy in the category topological spaces. This is a shorthand notation that will come up later in this video. An example of a category is the integers with this partial ordering less than or equal to. So in some general notion of a category, we can say that numbers in the integers are the objects in the integers, are the objects of the integers. And then we have, in this particular category, we have the homomorphisms between two of these objects in this category just less than or equal to. So we have n is less than or equal to m, or m is less than or equal to n. And there can only be one for any two of these integers. You can't have more than that. You can either be equal, less than, or equal to. Another example of categories is we have pointed topological spaces. In the last few slides we saw topological spaces, but we can also think of topological spaces together with a point x that lives inside of these topological spaces. So the objects of this category are just x together with some x naught that is contained in that x. And then the maps between these pointed topological spaces are just similar continuous maps that map one to the other continuously. Now we can think of the category cat. where we have the category of categories, and the objects are categories, and the maps between these categories are something called functors. So now let's take a look at what it means for something to be a functor. So for two categories C and D, we have a functor is this map that takes C to D, such that F applied to the composition of morphisms is just the composition of the map applied to the morphisms, and the identity for some category, for some object in the category of C, when you apply F to it, just equals the identity on Y that it maps to. And this is for X and C and Y and D, and we call this a functor. So we can think of a functor as something that maps one category to another. And to see this concretely, let's take a look at a very special functor. So we have a set of numbers in a group, and a group is just a set of numbers plus a binary operation. What we can do is we can define this thing called the forgetful functor, where we say, okay, just forget about the binary operation, then we just have a set of numbers. And this is a map that takes you from the category of groups to the category of sets. So similar to this is we can look at this functor G, which is this next example, that takes you from sets to groups. And this is just the free abelian group generated by the sets of the elements of the set. So let's look in the category topological spaces and the category of sets. We again have this forgetful functor that takes you from topological spaces to sets, where you just forget the structure of the open sets and just look at it as a set of numbers. Now from the category of sets to the category of topological spaces, we can always take a set of numbers and form a topological space called the indiscrete topology. The indiscrete topology is when you just assign the set and the empty set to the set of open sets. Similar to this, but a little bit more emphasis, is we can also define the discrete topology for sets, where we just define the open sets to be the singleton sets for each of the xi in a set S. So we have these two functors, G and H, and then we have the forgetful functor. And what we can say is we can say that these two functors are adjoints of each other. So we also have that the forgetful functor is both a left and a right adjoint in the category topological spaces, and it is left and right adjoint to the indiscrete topology and the discrete topology. The next element we need in this to define sheaves, we need to define natural transformations. So the motivating example for a natural transformation, it comes from the category of finite dimensional vector spaces. If you take two objects in this category and we look at the dual space, well, we have that there's always this isomorphism from V to its dual. And similar, if you just apply the dual operator twice, you just get you get the first vector space back. So what we're going to do is we're going to find this functor where you take the double dual of a vector space. And sometimes we write functors like this where we just apply the operation to some empty variable where I have the hyphen inside of the brackets. And that just means that we're going to take that and apply it to V or W. And then what we get is we get this also trivial functor where we just go back to the vector space itself. So if we write this in terms of the dual functor, what we get is we get that F, this trivial functor, takes V to W, and then we have that these are both naturally isomorphic to the functor of the dual applied twice to these vector spaces. And the fact that this whole diagram commutes, that means that this is a natural transformation. So when we define a natural transformation, we just look at two functors. And what we'll say is, we'll say that there's some natural map that takes the application of one functor to the application of the other functor. And when this whole diagram commutes, and we have what this means to commute, we have that n of y composed with f applied to f equals g applied to f equals composed with nx. So these maps here that take f applied to x to g applied to x and then f applied to y, there's this ny that takes it to g applied to y. And when this occurs, we say that there's a natural transformation between these two functors. So we'll also write the natural transformation with this implication symbol. So when you see the implication symbol f goes to g, we're going to say that that's a natural transformation. And this happens exactly when this diagram commutes for two functors. An important example of this is in R modules. When you have an R module homomorphism from M to M prime, then what we have is we have this natural transformation between these two functors, where the functors are the set of homomorphisms from M prime to some other R module, and this is naturally homomorphic to the homomorphisms of M applied to some other R module. So if you think of this as any R module, and then you take some other left R module, N, and you apply this tensor operation, and then you get that this map commutes. So what we get is actually this set of homomorphisms as a natural transformation. And we also have that there's some idea of adjoint here with the tensor product. Another important example of a functor is we have G and H are groups, and we want to go from groups to abelian groups. So what we can define is we can define this functor G superscript AB, and what that's going to do is we're going to take G and we're going to mod out by the commutator of G. So we write this functor like this, and we have G superscript of AB with this bracket notation. That's going to take groups to abelian groups. And what we're going to get is when we do this, we're always going to have some natural projection map that's going to take the group to the group module its commutator. And once we apply a group homomorphism from H to G, we get that this whole diagram is going to commute. So we get another good example of a natural transformation, of why we call this natural. So next, let's define a category of functors. Okay, so if we have a category of functors, what is a morphism between the two functors? Well, the morphisms between the functors are exactly there. We define a morphism whenever there's a natural transformation between the functors. So now let's look at the category of topological spaces. And for the sake of this video, we can define sheaves and sheafs much more generally, but let's just do it in the context of topological spaces. So if you have a topological space X, and we're going to define the category of open sets, and the objects of this category are just the open sets of X, together with morphisms that are inclusions. So if we have this setup where we have that U is contained in I, and we'll write this with an I, but this just means that U is contained in V. So now let's look at what happens when we look at the continuous maps that are defined that map an open set U to R in some continuous way. If you see here, we have that U is contained in this larger set V. Well, then what we have is that for the continuous functions that are defined over V, we can introduce like discontinuity there. This is no longer a continuous function. So what we can see is that there's actually more continuous functions as we shrink these, as we shrink the size of the open set. So because there's more continuous functions as we shrink the sets, is what we can actually say is that this F is a functor, and whenever you apply this functor to these open sets, you get this flipping of the arrow, and we call that a contravariant functor, because occasionally the arrows will go the same way, but often in this sense they flip. So F is a contravariant functor from the category of open sets of a topological space, and it can just go to some category. We can think of these functions as an abelian group. We can think of them as a ring. We can think of them as a vector space, and basically what category we decide to map it to is whatever category we think is useful for our purposes of study. So if you look at this diagram I have here, we have this larger topological space X, and then we have these two open sets that are contained within X. We have V and then U. And then we have these functors applied to these open sets that sort of live above them, which are the continuous maps. And then what we're going to focus on is what happens at these intersections. And this is going to help us define a sheaf, but first we need to define a presheaf. To define a presheaf, what we're going to have to do is we're going to have to look at these things called restriction maps. So if we have this larger set, this larger open set, and then this one contained within it, what we're just going to look at is when we restrict these functions over it to these smaller sets, this is what the restriction map is going to be. And what we're going to do is we're going to pose this condition that the restriction map from U to U is actually just the identity on U. So for the sake of this video, let's just look at topological spaces because this is the easiest one to get. And just make a note that they get much more complicated as these spaces get more general. And they're used in all different sorts of fields like de Rham cohomology and also in just lots of places. So we're going to look at, for topological space, and this function or this functor f applied to the open sets, we're just going to consider it to be abelian groups because that's the easiest one to work with. We're going to say it's defined by these following conditions. For each object in the open sets, there exists an abelian group where we're going to just apply that functor, and then the elements, that's going to be an abelian group because we just decided it was an abelian group. So the elements of this functor applied to this open set are called the sections of f over U. In this video, we're just looking at the functions, the continuous functions, but these can be much more general depending on what your underlying category that you're looking at them in is. And because we're looking in topological sets in the category of open topological sets, the category of open sets in topology, we just think of these as functions for the time being. That's where the intuition comes from. So for each set that's contained in some open set, we have that the restriction map restricts the functions over that space to the smaller set. So if there's this inclusion, we get that this map goes this way, and remember it's a contravariant functor. And then we also have that, as defined previously, we have that the restriction map defined to U is just the identity on U. And then we have, if there's some smaller subset W that's contained in V, that's contained in U, then the restriction map of W to U is just the composition map, just the composition of the previous two composition maps. So we can think of this as if we have these inclusions, then we get that the functor applied to these inclusions just reverses the arrows. So the arrows go this way, and these arrows are going to go this way. And this arrow should go this way. That's a mistake. But that's what it means to apply this contravariant functor to this setup. And this is how we define a presheaf. So now let's define a presheaf with a few extra conditions. The first condition we're going to impose additionally on these presheaves is that we're going to take an open cover of the space, and we're going to take some section f sub I in any of the functors applied to some open set in this open cover. And we're going to do this such that on the intersections of this open cover, we're going to have that this function restricted to those intersections is equal. Well, then what the gluability condition is going to tell us is that then there exists some f in the total space such that this function f restricted to each of the open sets equals the function that is restricted on the intersections. So it's better to look at this as an example. If we take X to be the union of three open sets, and we have that on these intersections they agree, well then we say there's some global function f, and we say that there exists an f such that f sub I equals f restricted to each of the open sets. And that's the meaning behind the gluability condition. So before with pre-sheaves, we didn't have this condition because we could have just wonky sections that aren't necessarily doing this. But if we look at this restriction of these conditions down with this gluability conditions, we suddenly get more in our sheaf. The second condition is going to be uniqueness, and this is also sometimes called locality. So if we have two sections in this total space such that they're equal restricted to every open set, then we have that they're actually equivalent. And to see this, we're going to look at a non-example to see what it looks like when this condition fails. So if we look at this example, if we have that these two functions are agreeing on both of these open sets, then we have that they have to agree in the total space, and this is the uniqueness property. So locally they're equivalent, so they're part of the same function, and this is what it would look like if it wasn't this. Then these two functions wouldn't be equal, but they agree on all the open sets. And this is a sheaf. We have a pre-sheaf that obeys these two conditions, and then we have a sheaf. So here's an example of something that is a pre-sheaf but not a sheaf. If we look at the continuous functions that are bounded on R, on the open sets to R, well, let's take an open cover of R, and we'll take u sub I equals I minus 2, this open set, I plus 2, for each of the integers I. Well, clearly this is an open cover of R, and it goes all the way to infinity and back, to infinity and beyond. So then suppose by uniqueness there exists some S, and we're using S for section now in this functor applied to R, such that S restricted to each of the open sets equals u sub I for I in the integers. Well, then by our hypothesis, if S is in our pre-sheaf, we have it's bounded. Well, then this means that there's a K such that the supremum of S is less than or equal to K over R. But then this is a contradiction because you have that it's going for every open set all the way here, and then there's some K which it's not, it's less than here. But it has to be defined here and so on. And then this has to be a contradiction. It just can't be a sheaf. So we see that these functions are contained in the sheaf, but we don't have enough functions to make it a sheaf because there isn't this uniqueness property will break down. So let's look at a sheaf from a farmer's perspective, because I am but a simple farmer. And we have this topological space X, and then we have this stalk, and this stalk projects above the topological space, and then we have this thing called the germ, and the germ is this little Quaker Oats thing that spans off of the stalk, and it's what they make flour out of. And this is the general idea of what a farmer would think of a stalk or a sheaf, and this is a sheaf of wheat. So we have this analogy where we have these things, and these are these rings or abelian groups that are coming off the topological space. So we look at that, but now let's see what a germ is. So here, as we have these open sets, and these open sets kind of collapse, these open sets get smaller and smaller. We want to look at what happens as it converges towards a point x naught. But x naught is closed in the real number, it's a singleton. So the functor applied to this closed point doesn't make good sense. So we sort of notice that the sheaf structure is capturing some notion of an infinitesimal because we're getting the shrinking of the real number line towards this point. So we want to encode this information and this data in our sheaf structure. So what we're going to do is we're going to look at this f subscript x. Because we can't actually look at the point close, what we can do is we can form all the open sets around the point and just write this x subscript x to be the set of f. It's going to be the tuples of f and open sets u, such that x is contained in u, and the section of f is contained in the functor applied to that open set over u. And we're going to call this a stock. Next, what we're going to do is we're going to define an equivalence relation. We're going to take two sections, f and g, with the corresponding open set that they're defined in the functor over, and we're going to say that these two tuples of sections and open sets are going to be equivalently related if there exists some other open set in the intersection where they're equal. We're going to call this the germ. So if you think of this as the little Quaker Oats analogy, we have the stock and then these germs coming off, and then this is all over the set X. So if we have X a topological space, and we're just looking at this in the sense of topological spaces, then we have a pre-sheaf on F is precisely a functor that takes the opposite category of open sets to sets. And the opposite category, we didn't talk about this, but if you have sets of morphisms that take you from one object to another, you just say those two objects have a morphism in the opposite category if they have a morphism in the original category. So the objects in this category of pre-sheaves is just the functors that have a natural map between them. So we have that in this category of pre-sheaves. We have G is naturally transformation to F. Those define our morphisms in the category of pre-sheaves. And there's a little bit more work to do here where we have to show there's identity and such, but for the purposes of this, we're just going to note that there is a category of pre-sheaves, and then we're going to just define the category of sheaves on X to be the subcategory of pre-sheaves where the objects are also sheaves. So a good example to see how this works is if we have a smooth manifold and we have a tangent space that projects off of a point, we're going to look at this sheaf over these open sets where it's just going to be the set of infinitely differentiable continuous functions over the open sets to take that open set to R. So there's lots of functions out there that are, they always have a derivative and higher derivatives. And this defines a sheaf. And if we localize this sheaf at the point, what we're going to get is we're going to get a local ring. And this local ring has a unique maximal ideal. So a lot of times in algebraic geometry, when we take this maximal ideal and mod out by the unique maximal ideal, because it's a local ring, what we get is we get a k-dimensional vector space. And right now we're just looking at this over the real numbers, so we'll just call it a real vector space. So in algebraic geometry, a lot of times in the textbooks, they'll just say, oh, the tangent space is equal to the, and this should be the dual here, because this is actually the cotangent space. You have that the maximal ideal modded out by the square of the maximal ideal is the tangent space. So by taking that dual, we get the tangent space. And this is another way to look at the tangent space that is localized around the point and we consider as a local ring by looking at this as a sheaf. So this is one application of this sheaf theory that comes quite in handy for physicists and other areas in applied math. Another good example that comes up is we want to look at a graph, and our graph will have these nodes, V1, V2, and V3, and there's like some connection between them. Well, what we can do is we can embed this space in R2 or R3 and then look at these vertices as just points. And we can look at them as points. And then what we get is because this inherits the subspace topology of Rn, we can draw open sets over each of these. So we have an open set, an open set, open set. And this allows us to encode more information about the network structure than we just get just looking at this as a graph. So we can now think of each of these points as having this vector space F, U, applied as a functor over them. And then this gives us the linear maps between these points in our graph. And there's recent work that looks at the opinion dynamics of sheaves. And this all works because you can define these open sets in the real numbers, and then you can look at the linear maps between them. People have this work even defined a sheaf Laplacian by looking at the network structure and then defining it within the real numbers as such, and then you can look at how these dynamics evolve. Another good example of sheaves is from data science. So you have this idea of how all these data points are related, and these can be elements in a database. For example, you do a query of a database, and you get a column back, and this will be R2. So you have some number here, some number here. And this could be some real concrete data point, the GPA of a student, the number of scholarships, etc., etc. And these can have all sorts of associations to how well they'll perform. It could be that this is their data from when they were in high school, college, graduate school, and then they're all related in this way. And then this gives us the associations between all the data points, along with restriction maps that take us from one of the data points to another. And this is all a sheaf is. You have some network structure, you have maps between them, restriction maps. You can look at continuous maps. You can look at them as infinitely differentiable functions over manifold, where you reconstruct ideas about the tangent space at a point by localizing. And the whole point is sheaves are cool. Thank you for watching. I hope you enjoyed it.